Hello, everyone. Welcome to the April 7th edition of MathStats. Quick reminder, your project updates are going to be due on Thursday. So we are not going to have a lecture for Thursday. We're still going to have class, but class is going to be spent in your groups working on your project updates and allowing you the opportunity to ask me any questions you have about what my expectations are for that. So be sure to keep collecting survey responses from whoever you can, as long as they fit within the purview of your project. All right, so last time we talked about Neyman Pearson, and I apologize that lecture was so long. I was trying not to make it long, but I wanted to make sure that you sort of have as many examples as possible. Now, Neyman Pearson is a lemma that is an approach to how you come up with the best critical region that you can, and it's a required topic for the class from the SOA. So that's why I wanted to make sure we covered it and gave you a sense of why we care. So Neyman Pearson was for distributions with one parameter, but sometimes our distributions have more than one parameter. The normal distribution has two parameters. The gamma distribution has two parameters, so we need a way of addressing those distributions. So we also need to address the situation where we have hypotheses that are both composite. Remember that for the Neyman Pearson lemma, we had to have two simple hypotheses. Our null hypothesis said that the parameter was equal to something, and the alternate hypothesis said the parameter is equal to something else. So going through today, we're going to switch up our approach slightly. Our PDF or PMF of our function is going to be written as f of x theta, even if you have multiple variables and theta could represent multiple parameters. Kind of like mu and sigma squared are different parameters for the normal distribution. So big omega is the parameter space for theta. That is, big omega is the set of all possible parameter values. So we're going to let our null hypothesis be that theta is an element of lowercase omega, and the alternate hypothesis is that theta is an element of omega prime. This is the complement of omega, little omega. Okay. So note that little omega is a subset of big omega. It's a subset of possible parameter values. So an example might be that big omega is the set of numbers from negative infinity to infinity. Maybe lowercase omega is the numbers from negative infinity to 2, and therefore omega prime would be the numbers from 2 to infinity. So this is how we think about it, because often we don't actually know what the mean of the distribution is. We just kind of want to know if it's lower than something or bigger than something. Okay, so we need to define something today called the likelihood ratio. This is going to extend our idea from Neyman Pearson. And the likelihood ratio is lambda is L of omega hat over L of big omega hat. And you're probably wondering, what the heck are these things? So do you remember when we calculated maximum likelihood estimators way back towards the beginning of the class? Well, they're making a reappearance today. This is the maximum of the likelihood function. over the possibilities in little omega, and this is the maximum of the likelihood function over all big omega. So L of big omega hat, that's the maximum likelihood estimators that we found back towards the beginning of the class. And the big L of little omega hat, that's a little different that we'll talk about today. So there's a couple things we need to observe. So the likelihood function L is a PDF or PMF, which means that L is always between 0 and 1. So the first thing you should observe is that theta is positive because, or 0, because L is a function that's always between 0 and 1. So if I divide them, it should be positive or 0. This tells us that lambda is bigger than or equal to 0. However, we know that this value must be less than or equal to this value. Why is that? Well, we know that L is a function of theta hat, of omega. And omega is an element of this space. And so basically what's happening is little omega is a subset of big omega. So that means that what that looks like is here is our domain of our function. Maybe here is little omega, and the whole thing is big omega. And so if I find the maximum of the function over here, the maximum, it gives us this value right here. But it's possible that there's a bigger value over here. So what that tells us is that since big omega is a bigger set than little omega, the maximum of my function L over big omega must be bigger than or equal to the maximum of my function over little omega. Okay, what's that to tell us? That's mostly to tell us that lambda is less than or equal to 1. So overall, lambda is a ratio between 0 and 1. Okay, so why do we care about this? Well, we have kind of two philosophies that dictate what's going on. If lambda is very small, what does this tell us? Well, what this tells us is that the maximum of L in omega, little omega, is smaller by a lot than the maximum of L in big omega. And what this suggests is that our data does not support the null hypothesis. And then we would reject the null hypothesis in favor of the alternate hypothesis. Think of this as some kind of probability. If lambda is very small, this is suggesting that the probability of our sample landing in little omega is very small. All right, but if lambda is close to 1, this would lead us to believe that we should not reject H0. Okay, so that's kind of the idea. So we need one more definition. To test our null hypothesis against our alternate hypothesis, the critical region for the likelihood ratio test is the set of points for which this ratio is less than or equal to k. Okay, so this should really remind you of what we saw in Neyman Pearson. We see that we have some quantity and we want it to be less than or equal to some value k. And you see this likelihood ratio appearing again. Looks a lot like what we saw last time. Okay, so I'm going to go through the two examples in the book because I think they're kind of hard to understand the first time you read them. So what I will do is I'll go through them and then you can reread them at some point to get an understanding of what is going on. And essentially what we're going to be doing is we're going to show you how the critical regions that we're getting are going to be the same as the ones that we saw in the past using this new theorem. Okay, so let's do an example where X is the weight in ounces of a 10-pound bag. And they're not all 10 pounds, surprise, surprise. And we know that X is normal. We don't know the mean, but we know the variance. And we're going to test the null hypothesis that the mean is 162 ounces against the alternate hypothesis that the mean is not equal to 162 ounces. All right. So what is our parameter space? Well, our parameter space is what could the mean be? And we're just going to say the mean can go from negative infinity to infinity. We know the mean can't actually be negative, but for the purpose of this, we just don't really care. And little omega is 162. That's what's coming from the null hypothesis. And obviously then the complement would be that mu is not 162. All right, so we need to find the likelihood function for omega hat and big omega hat. So when the null hypothesis is true, there's only one possibility for theta. There's only one number in the little omega. So what this tells us is that L of little omega hat is just we plug 162 into the joint PMF or joint PDF. Okay. So the question though that's more pressing is, what is L of big omega hat? Well, we just need to know what the maximum likelihood estimator is. And we know that the maximum estimator from previous chapters is just our sample mean. So what this tells us is that we just need to plug an X bar into the joint PMF, and then we'll get what we want. All right, so reminder, the joint PDF of these variables is a product from I equals 1 to n. And it will look like 1 over sigma root 2 pi e to the negative xi minus mu squared over 2 theta squared. Okay, so that's the joint PDF, and now we need to plug in what we have. So we're going to plug in 162 for mu, and that's how we get L of little omega hat, and we're going to plug in x bar for mu. That's how we get L of big omega hat. Okay, so we do that, and we find that lambda is this terrible looking expression. Oh, we also know that theta squared is 5. So there's a lot of algebra that goes on here, but I'm just going to write this out, and you can trust me that the algebra works out. We have this exponential, this gigantic expression. Okay. So we can simplify it a little bit. We see that these clearly cancel out. And now we do a little bit of algebra. So the denominator will stay the same. And the numerator we're going to slightly alter. Okay, so there's some algebra going on here. It's actually not too hard to understand. So what we see then is these, so what we're going to get is, if we simplify just a little bit more, this is the exponential of negative 1/10 times this sum. Oh, it should have been xi's. My bad. Okay. See that these cancel out. And what I'm left with is this exponential. Okay, so we need to make some observations about this. So if x bar is close to 162, we see that lambda is close to 1, because this would be 0 if x bar is 162, or close to 0, and we know that the exponential of 0 is 1. But if x bar is far from 162, we see that lambda is close to 0. Because, again, if the underlined part is big and we square it, then this whole thing is going to be negative, and the exponential of a large negative number is very close to 0. All right. So in this first case, where x bar is close to 162, this case supports our null hypothesis. And this second case supports our alternate hypothesis. So we want to manipulate this to find a critical region of size alpha. So lambda is this thing that we don't really know much about, but we need to find a critical region of size alpha. So we need to select K to make this work. Okay. So what are we going to start with? Well, we start with this same inequality right here. We start with the exponential. We want this to be less than or equal to K, and we're going to manipulate this until we get something that we are used to. So we take the natural log of both sides. We multiply both sides by 10 over negative n, and that switches the order of the inequality. And then we take, what we're going to do is, it's a little hard to see, but what this tells us actually is that the absolute value of x minus 162, this must be bigger than or equal to the square root of this guy. And then we divide both sides by root 5 over root n. And that's what we pick for C. So why do we care about this? Well, this should look very familiar. This you should recognize as coming from the critical regions in the past we defined for a two-sided test. So what's happening? Well, here's our normal distribution. We pick this under the hypothesis of mu equal to 162. So the mean is 162. And we picked our C so that if this is x bar down here, and this is lambda right here, this distance is actually C times root 5 over root n. And what we actually find is that this is the value of K we picked. And see, and this is 1. And so this is how these different parameters are connected. So how do we know this? Well, we know that the standard normal follows this distribution. And that's the normal distribution with a mean of 0 and a standard deviation of 1. So how do we find C? Well, we just let C equal Z alpha over 2. Z alpha over 2 is what gives you alpha in the left and right tails combined. And what this tells us is that our critical region should be the sample means that give you a quantity bigger than or equal to Z alpha over 2. So let's do a little example, and you'll see what I mean. As an example, if alpha is 0.1, you can check on RStudio that Z of 0.05 is 1.645. 1.645, negative 1.645. This tail has area 0.05. This tail has area 0.05. There's 0.90 in the middle. And this gives us a critical value. This gives us a critical region, which has area 10% in the two tails combined. So what was the point of solving for this? Well, this crazy long process right here, what this did was it showed us that this is the critical region that I circled coming from the likelihood ratio test. And we saw that it's equivalent to the critical regions we've been using in the past. So what this is showing us is that our previous ideas of what should be the critical region are actually the same as the critical regions for the likelihood ratio test. So we see that this new idea that we introduced produced the same kind of critical region that we were using before to reject the null. Okay. So that was an example that was a little bit, different because we assumed that we knew the population variance, which we never do. So I'm going to spend the rest of class deriving the following one. What do we do when we do not know the mean or the variance? So we take a sample, and we know that our population is normal, but we don't know the mean, and we don't know the variance. So we're going to find the likelihood ratio test critical region for the null hypothesis, mu equals some mu naught, against the two-sided alternative hypothesis that it's not mu naught. So omega, little omega, is the set of possibilities where the mean is mu naught and we don't care about the variance. And big omega is just, we don't care about either of them. They can be whatever they want. Except, yeah, they can be whatever they want. Okay, so this was, remember, this is the parameter space. That's the set of all possible values for mu and sigma squared, and we know that mu can be anything and sigma squared has to be positive. Okay, so if we're looking at the whole parameter space, then we know that the maximum likelihood estimators are x bar for the mean, and it's this expression for the variance. Okay, so what does this tell us? This tells us that if I plug this into our equation for the joint PDF, it's going to look bad. So bear with me for a second. We see that these cancel out. And what we're actually left with, if we do a little bit of simplification, is this lovely expression right here. And in a similar situation, if you're looking at little omega, our maximum likelihood estimators are, this must just be mu 0, because that's the only possibility. And our estimator for the variance is the same as before. It's slightly different because we know the mean. Okay, so what does this tell us? This tells us that if we plug this in into our likelihood function, which is the joint p df, we're going to get some similar looking expressions. I think I wrote this incorrectly before. That's an n over 2. There we go. And we get some similar calculations from before. Okay, so we did a lot of work. And so why did we care about this? Well, we needed to establish what the likelihood ratio was. We have these two lovely expressions. And we see that we're going to get some cancellations again. And what we're left with is this expression right here. Okay. So what do we do with this? Well, we need to do a little bit of side calculations. And what we see is that this sum simplifies to the following. Okay. Okay. So what we can do is we can plug this in to the denominator. And what we get is the denominator simplifies to I simplify that a little bit, it becomes 1 over 1 plus n x bar minus mu 0 squared over the sum. Okay, so you're probably wondering, why on earth do we do that? That looks terrible. How could that possibly be any better? Well, we know that this thing on the right is less than or equal to k. So let's take the natural log of both sides and start solving for what we need to solve for. So take the natural log of both sides and divide by n over 2. So this tells us that this lovely expression is less than or equal to 2 over n times the natural log of k and the left-hand side has a natural log too. So if we kind of exponentiate both sides, what this tells us then is that this expression on the left is less than or equal to k to the 2 over n. All right, so multiply through both sides, clear the denominator. This tells us that 1 is less than or equal to, k to the 2 over n times this expression. And then we divide both sides by k, subtract 1. All right, so we're getting close. Still not there yet, though. The last step is actually to multiply both sides by n minus 1. Okay, now you're looking at this expression, you're saying, how on earth is this relate to anything? How does this relate to anything that we've done so far? Well, here's what we know. What do we know? We know that x bar minus mu 0 over sigma over root n, which is the same as x bar or root n times x bar minus mu 0 over sigma. This is the standard normal variable. We know that x bar is normal with mean mu 0 and standard deviation sigma over root n. We also know that this expression this comes from chapter 5. This is actually a chi-square variable with n minus 1 degrees of freedom. So under the assumptions of our null hypothesis, what this is telling us is that the t variable which has this expression if I simplify it, it looks like this. The sigmas are going to cancel out. And if I just write this in a slightly different form, this is x bar minus the mean over the sample standard deviation over root n. And you probably recognize that. This is a t distribution with n minus 1 degrees of freedom. So if I look back at this expression right here, and this inequality, this is telling, I see on the right-hand side that this is actually the t squared of what I described below. So this is telling me that my critical region is t squared bigger than or equal to n minus 1 k minus 2 over n minus 1. And so what we say is then, this is telling it, we say that this critical region right here looks basically like the kind of critical region you would choose. And so we're going to pick this to equal t alpha over 2 with n minus 1 degrees of freedom. I think we're going to do it squared. So we're going to reject our null hypothesis in favor of our alternate hypothesis if the absolute value of t is greater than or equal to t alpha over 2 with n minus 1 degrees of freedom. So what is it that we did? What did we do? We started way up at the top with this crazy expression. We're almost there. We started right up here with this expression. And we wanted it to be less than or equal to k. And we did a ton of algebraic manipulations. We manipulated it, we manipulated it, and we manipulated it. And at the very end, after all that work, we said that, okay, our critical region must be the same as this. T squared must be bigger than or equal to something. And we can pick what that something is. And that something is exactly t alpha over 2 with n minus 1 degrees of freedom squared. And so what that's saying is that the critical region defined by this likelihood ratio test is the same as the critical region that's defined before. And so what this is telling us is that actually all of these tests we've been doing for the mean, so the takeaway is that all these tests critical regions we learned about before are actually likelihood ratio. So all those tests from before coincide with what we learned today. All right, so this is pretty abstract, but the idea is that we take this concept to sort of choose choose how we're going to pick our critical region, and we show that that thought pattern gives us the same critical regions that we came up with from before. Let me know if you have any questions, and I will see you soon.